Hey guys, welcome back to chapter 11. In the last video, we covered the first of the colligative properties, and that was vapor pressure lowering. In this video, we're going to talk about boiling and freezing point. They are very, very similar to one another, so we just kind of talk about them in tandem because there's so many similarities. So in the last video, we talked about this idea of vapor pressure lowering. Now what we're going to talk about here is boiling point elevation and freezing point depression. So as I said before, we kind of give away the answer, right, in the name of it. So when we're talking about the boiling point of a solution, so remember we have a pure substance, we have water, just H2O, nothing in there. It's got a certain boiling point. Now we're adding some sort of solute particle to that solution. We're making a solution, and that's going to change some properties. That's what colligative properties do. And remember, we are interested in not what we put in there, but how many particles are in that solution. So boiling point elevation, a solution will boil at a higher temperature than that of its pure solvent. Okay, so for example, water boils at 100 degrees Celsius. If I were to add some sort of solute particle to that water, it is now going to have to reach a higher temperature in order to boil. So it may be 100.5, it may be 103 degrees, but some temperature that's higher in order to boil. That difference in the boiling point between the solution and the pure solvent is called boiling point elevation. And it's denoted with this triangle symbol, the delta symbol. So remember that triangle just denotes change, or it's a symbol for the word change. So the change in temperature, and then we use this subscript B to indicate boiling, because we'll look at freezing, it's very similar. So the change in temperature of the boiling point, that is that difference between 100 degrees Celsius and maybe 103 degrees Celsius. So that would be a 3 degrees change. For the freezing point of a solution is lowered than that of a pure solvent. So again, if we stick with our water example, pure water freezes at 0 degrees Celsius. If I were to mix some sort of solute in there, doesn't matter what it is, just matters how much. Now that water is going to have to get down to -1 degrees or -5 degrees Celsius before it becomes a solid. And then the difference in the freezing point of a solution and the freezing point of a pure solvent is called freezing point depression. And it's denoted with that same symbol, that change in temperature, and this time we use a subscript of F because it's a freezing point. One other thing to note here is that when we calculate, and we'll do this in just a moment, when we calculate the change in temperature for boiling or the change in temperature for freezing, both of those will be calculated as positive quantities. It is up to us then to decide, are we adding that change to the boiling point? So whatever this value is, we would add it because it raises the temperature. Or are we subtracting that change in temperature? So if the change in temperature for freezing is a positive number, we know that's going to be subtracted from that original freezing point because freezing point temperature is lowered. So both of these are going to be positive quantities. It's up to us to decide, do I add it, do I subtract it? So let's take a look at the equation for each of these. We are going to be able to calculate the change in boiling point, the change in freezing point. So here is our formula for boiling point elevation. So the change in temperature for that boiling point is going to be 3 different variables all multiplied together. So the product of 3 variables. The first variable is a boiling point elevation constant for that particular solvent. So water will have one sort of constant, ethanol would have another constant. So this is for our given solvent. The next one is that unit for concentration that we just introduced. So that next one is molality, right? So that was that new unit of concentration. And then the last one is this thing called a Van Hoff factor. So we'll break down what this I means in a couple slides from now. But as long as we know all three of these pieces, we can multiply them together, and that will change, or that tell us how much that boiling point is going to change. The reason that we introduce these two in tandem is what you will find is the formula for freezing point depression is almost identical. So we've got the Van Hoff factor, that's the same. We've got molality, that's the same. We've also got some sort of constant, but of course this is the freezing point depression constant, but nonetheless it's still the constant for the solvent. So what you'll see is these formulas are almost identical. That's why we teach these two in tandem with one another. All right, so let's get to know these variables a little bit better. We did molality already in a previous lecture. So now let's get to know these other two before we dive into an example. The freezing point depression constant, or the boiling point elevation constant, is just that. It's a constant for a given solvent. It's something that's going to be given to you in a problem. It's never anything you'll have to memorize, or it's something you'll solve for. But nonetheless, it's nothing you'll have to memorize or come up with out of your brain. The constants here represent a vulnerability to change. So these constants tell us how vulnerable our solvent is to changing when we dissolve a solute in there, okay? Something that has a big K value is going to be vulnerable to large changes. Something that has a smaller K value will be resistant to change. So if we look at the boiling point here, we see that water has the smallest value for K. That should not be surprising at all, as we know water is resistant to change, right? So if you think back to when we talked about heat capacity, right? Water has a very, very high heat capacity. It's going to take a whole lot of work to change that temperature of that water. And we see that reflected here in the KB value. It's got the lowest of all of these. Looking at our chart here, we see nitrobenzene has the highest KB value. So this guy would be the most vulnerable to a large change. So we might see a much larger change in the boiling point for nitrobenzene than we would for water. So that's just a little bit more about what this K value means. And then again, these are going to be given. One last thing to note on this slide is the unit for KB. It's kind of a wonky, weird unit, but the unit is degrees Celsius per molal, or degrees Celsius over molality. That seems like a weird, wonky unit, and it is, but when we start mathing with this, it's going to be very convenient. So that's the unit for the KB value, degrees Celsius over molal. All right, so the last variable, that Van Hoff factor, that I factor. Remember I talked to you guys about the fact that colligative properties depends on the number of particles, not necessarily what we put in there, but how many we put in there. We've got one variable already that's addressing the amount of particles, and that's molality, right? That's a concentration. So the bigger the number for molality, the more particles, smaller the number, less particles. Well, Van Hoff also recognizes the number of particles. And so what this is looking at is, well, what happens to those solute particles when they dissolve? How do they dissolve? So for solutions where we put electrolytes into solution, we have to take into account the fact that electrolytes dissociate or break apart. So just as a refresher, what is an electrolyte? An electrolyte is an ionic compound that dissolves in water. So electrolytes are notorious for dissociating or breaking apart into their ions. So our poster child for electrolytes is sodium chloride. So sodium chloride is sodium and chlorine attracted to one another through electrostatic attraction. When I put a sodium chloride particle into solution, it will dissociate or break apart into its ions. So if I look at one sodium chloride, when I put that sodium chloride into solution, it's going to break apart into sodium ion and a chlorine. Oops, that is a negative. And a chlorine ion. Okay. So when I put one, let's say, molecular unit of sodium chloride, it's going to break apart into 2 particles in solution. Van Hoff factor identifies this process. So the Van Hoff factor for sodium chloride is going to be a value of 2. I put 1 particle in, but when it dissolves, 2 particles are in solution. Okay, so here we see 4 particles going in, but after they dissolve, we count 1, 2, 3, 4, 5, 6, 7, 8 particles in solution. So we put 4 in, but 8 are separated in solution. Okay, so that is the Van Hoff factor. I think Van Hoff is easier to think about just kind of from a conceptual standpoint. I think it's harder to use the formula I'm about to give you, but I'll give the formula nonetheless. So Van Hoff factor is calculated by the moles of formula units, so the amount of sodium chloride going in. And on top of that, we're going to put the particles that we would see in solution. So for example, if I put 1 formula unit of sodium chloride into solution, there's going to be 2 particles in that solution. So the Van Hoff is a value of 2. Okay. Van Hoff is a theoretical, so anytime you have to decide what Van Hoff is, we're going to use this theoretical value, which is a nice whole number. In reality, Van Hoff may be like a decimal. It may not be exactly 2. It may be 1.9. But anytime that we're using it in a formula, just go ahead and put that whole number of 2. There will be problems that ask you to solve for Van Hoff, so solve for I. And if you come up with a number that is not a whole number, that's okay. That's to be expected. So let's think about a couple other examples of Van Hoff factors. So let's look at magnesium chloride. So magnesium chloride is MgCl2. When I put this into solution, how many particles do you think this is going to break apart into? Yeah, it's going to break apart into 3 particles. So we've got 1 magnesium. This subscript 2 tells me that 2 chlorines are in this process. So the Van Hoff factor for magnesium chloride is going to be a Van Hoff factor of 3. So when it's just a diatomic ionic compound, so just like a metal and a nonmetal, those are pretty easy. When it becomes tricky is when we start to do polyatomic ions. So what about something like magnesium nitrate? put magnesium nitrate, let me do it right first. When I put magnesium nitrate into a solution, it is going to dissociate or break apart. And the way that it's going to break apart is it's going to break apart into magnesium. And remember, these polyatomic ions are little packets of atoms. So this packet of atom will stay together. It does not break apart into nitrogen and oxygen alone. It will dissociate as a packet of atoms. So for this example, the Van Hoff factor for magnesium nitrate is also 3. We'll have 1 magnesium and then 2 of the nitrate particles. Okay? That's where things get tricky. Students often try to say the Van Hoff factor for this is like 14. We're not going to have Van Hoff factors that are that big. So let's take a look at a chart of just some common Van Hoff factors. So here we see that sodium chloride, the expected value is 2, magnesium chloride 3. Here we see a couple polyatomics. So this one has an expected value of 2. This one has an expected value of 3, right? One other thing to note about this chart is non-electrolytes. So non-electrolytes are like your sugar particles. It's your covalently bound compounds. When I put a non-electrolyte into solution, it's going to stay together. It's going to dissolve, right? But it stays together as one big particle. It doesn't dissociate or break apart. So anytime you hear the words a non-electrolyte in solution, you can just assume the Van Hoff factor is 1. All right, so now we've talked about all of the values associated with this boiling point elevation or freezing point depression equation. We've talked about molality, we've talked about this constant, and we've talked about the Van Hoff factor. In the next video, we'll go ahead and knock out an example of actually calculating the change in temperature. I hope you guys found this helpful.